Hi there, and welcome back to Triplicate and part 4 of the Mean Green synthesizer build. And yes, we're still at the stage of a board floating about on the bench. Last time we were trying to get the audio interface working, which we did do, but we couldn't get it working with the DMA, which we really need to do. And the problem with the DMA was a bug on CubeMX and the HAL, and I did a separate video on my investigations and solution to that problem. But now we have the DMA working, but we want it to work in circular mode, not what they call normal or straight mode, and I'll explain why. Okay, so this is how it works. The basic DMA, you fill your buffer and you tell the DMA to start, and the DMA plays through to the end and stops, and it sends you an interrupt, at which point you have to refill the buffer and start the DMA off again, which is fine, but it means you need to be able to calculate a full buffer's worth of samples in one sample period. We want the processor to be working hard, so we want to spend nearly all the processor time calculating our synthesizers so we can do as much as possible. So what we do instead is use a circular buffer split into two halves. Okay, so say the buffer is full of samples. The DMA will play through to 32 and then will send an interrupt saying the buffer is half used. It won't stop, it will continue playing the upper half, but we now know while it's doing that we can recalculate the lower half. And when it gets to the end of the upper half, it will automatically loop round, hence circular buffer, and start playing the lower half, which we've just filled, and we can now start calculating the upper half while it's outputting the lower half. So as long as we're calculating the samples at least at the rate they're going out, will be good. So the way we do this is we change the DMA from normal to circular. So the DMA now goes round in a circle forever, and we don't need to worry about it. So let us generate the code. Okay, so first thing is this line here. This solved the problem of the DMA not running. We enable the clock right at the start, and then all these functions down here, well, specifically that one, set up the DMA. Okay, so now let's go back up here. So DMA TX now can have several modes. It starts off as init, that then calls the DMA start function, sets the DMA rolling, and when we get a half callback it sets it to DMA TX half, and when we get a full callback it sets it to DMA TX full. When we need to write some new samples to the buffer, we call this write samples function. We give it a buffer which is stereo, and a count, which is a number of stereo samples to write, and that writes two triangle waves of 400 and 600 hertz, I think, something like that, which just allows us to see whether the thing's working or not. And we go into main, and in our while loop we now have a switch statement on this DMA TX. So if it's init, we just start the DMA going. Okay, so DMA TX is set to half transmitted in that little interrupt function, so we then write the samples to the first half of the buffer, to the bottom of the buffer, and at this point it's outputting the top half of the buffer, and when we get the full buffer full flag, we know we can send to the second half of the buffer because now it's transmitting the bottom half. So shall we try that? And yeah, I know I'm cheating because I know it works. So run debug. Okay, it's compiled. Let's run it and look at the oscilloscope, which is just set on the audio output. Yeah, and we can see we get two nice little triangle waves, and if I set the audio up, there's our triangle waves, a fifth apart. So that's good, that's working. So I think the next job is the clock. The reason we chose this particular processor is because it'll go at 180 megahertz. Now at the minute it isn't. Now this is the system clock frequency. So let us try and set it up so it goes to 180 megahertz. Okay, so here is the clock configuration. This is just another tab on CubeMX. And is this complicated or what? However, what we want is to change the sys clock here. And we want to get that up to 180 megahertz. And all these along here are the other clocks used by the system, and we want them to still be valid clocks. And I have had a play with this, and as you'll see at the minute we do something that is going to upset something, going to produce an invalid clock, it goes purple. So it's good, it tells us when we're doing something wrong. So we are going to get the PLL here, and we're going to change that to 360. Remember, we're trying to get 180 megahertz, so that gives us 90 megahertz. So we want double that. So we are going to take this and divide by 2. Okay, so now we have a couple of purple items over here. So we've gone too far with these, and you can see here it tells us what we're allowed with these, but it was alright at half that for the system clock. So if we divide both these by 2, they come back, we're good, and our I2S clock still 96 megahertz. So what do we reckon? Are we good at that? Shall we see? So I am going to hit generate code, and that's going to update with those changes. Now our project is open. We are going to get into the project. We're going to stop it, and I'm just going to build it. Okay, done. Every time you change anything in CubeMX, it recompiles a whole of the HAL, which takes over half a minute, which is why I spared you that. So shall we try and run that? Let us. Let's go into debug. And it reckons it's done that. Just fire it up and look and see what the scope's doing. Oh, that looks good. That looks good. I'll pull that back. Turn that up. So that's the time it's spending recalculating the sample. Okay, well I am going to assume that is good, with the proviso that the CubeMX has claimed it's done something that it's not done, and say we're looking at what, 4 or 5 microseconds to calculate 32 samples. And now we are going to press on. Okay, so next we are going to look at the analog to digital conversion for the pots. Now, it's thought to be straightforward, but there are two issues. Firstly, there are far more pots than there are analog inputs, and secondly, it's a matter of timing and interrupts. We already have 2 interrupts for the audio out, and we're going to get another one for the analog. And if we're not careful, we can get into trouble because it can be tied up in interrupts, waiting for other interrupts to go, and interrupts can be waiting for data from other interrupts, and we can get bugs which happen once in a blue moon given specific timings of interrupts. So personally, I like to have as little code as possible in interrupts, and set flags when something's happened that's caused an interrupt, and do everything in the main code. Right, so here we have our front panel. I've taken the 2 oscillator boards out, and there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 knobs, and not too many analog inputs on the STM32, because the only STM32F4 that was on the Nucleo board was this one, and I chose that particular flavour of STM32 because it was the only one that would do 180 megahertz clock speed. So, to overcome this problem, I propose to use analogue multiplexer chips, which you can buy pre-stuck on a board. I've got one here and I'm going to try it first, and I'm not entirely sure that's going to work, but we're going to try it, which means not only do we have to process the analog input, we have to set the multiplexer up to look at the right pot and look at each pot in turn. That's why I'm doing that next. It's a bit more complicated. Plus, I'm proposing to put the switches into the analog inputs as well, which is a bit overkill, but just actually simplifies the code and brings the total analog inputs up to 28, I think, which is 2 of these. So here are the 2 oscillator control boards, and I've made a start on wiring up, and I'm going to spare me soldering, so I'll just have the odd update on the wiring and come back when we're all wired up with that and ready to try and read some pots. Okay, so this is a bit with one of the pots, the switch and the 2 LEDs on. Originally I was going to take 1 ribbon cable off each board, but then that would have led to a lot of ribbon cables, well, twice as many ribbon cables as I am going to have, and each of them would only be half used, and it would be a bit spaghetti like. So I decided that after I, hang on, look at this all, put the connector on that, so that connector's not used, and I've wired up this end. This is the switch in one of the pots, and then those go like that. And I've wired up the supplies to the pots on this one. I've not cut some wires off, but I'll do that. And all I need now to do now is connect the wipers of these pots onto this connector, and the oscillator controls are done. And at that point I shall start trying to get the D2A working on the nuclear board on the STM32, just in case what I've decided to do turns out to be undoable and I have to completely rethink. Okay, another day over, sorta, and made a bit of progress on the mean green, so I thought I'd update you as to what I'd done. So we've got the oscillator control boards mounted back on and wired together, and got a ribbon cable ready to go down onto there. Got to get that on. Mounted the main board there, though that's going to have to come off more than once, I suspect. Mounted the audio output sockets in the back, and for now just used a 3.5mm jack into the audio output board, because we've got to take it all out probably on several occasions. Mounted it too far to the back, so it's a real pain to get that in. So that's just that's just a USB lead. I could do with a longer one. Got a piece of wire on the side here to stop it flopping back. I'm going to rewire the display, so like that one, it'll go down there and back, so in the front without pulling the plugs out. And got a MIDI interface. That's going to focus. A triplicate MIDI interface. Triplicate originally I was going to sell electronic kits under the triplicate name, but then I started working for somebody else again and there just wasn't a right lot of money in selling these, and it's a bit of a faff. It was fun to design something like that, but not so much fun just sticking components in an envelope and posting them. However, if you want one, I've got quite a few kits ready to go out. Well, ready to go out if I sort them out. So if anybody wants one, just let me know and I'll make you one up and I don't know, put it on eBay or some such. So that's it for today, and I'll I guess update you tomorrow when I've got a bit further on and I've got something more to report. Okay, it's been a couple of days, maybe 3 days since the last clipper video, so apologies for any non sequitur, as it were. So we're all in. Can we see that? Yes. And all wired up. These two wires, which you probably can't see, which be hand cam in this, I suppose. Anyway, there's two wires here for the LEDs, the oscillator select LEDs, which I haven't wired up. Apart from that, it's all wired up. Got this side of the meter connected to ground, so if I put this side of the meter, and we're just on ohms here, to ground, we get nothing, and this side of the meter to 3V3 we get 1.3 kiloohms, which is a few pots across the supply plus nuclear, so I'm going to take that. So dare we power it up? I think we're going to have to. So this, where I position this board, it's a bit tight getting that in, and this cable is a bit on the short side. So plug her in. Yep, the computer's gone biddly dump as though it's detected something. So I think we're good. So we're gonna put this meter into volts, and we are going to look on C0. Okay, so I can't work out a way of arranging it so you can see which output on here or input I'm probing on, what the meter's saying, and watch me turning the knob. So you're going to have to take my word for it that I'm turning the knob I'm saying I'm turning. So that, according to my spreadsheet, should be the Oscillator knob. And there we go. And that works. The second one shows the analogue. The second output is the detune, which is the next knob. So I put that on there. Oh, stay on. Okay, so I've connected the display back up and rewritten what was basically get it working display software to how I anticipate, hope it's going to work finally. So what happens now, because the display is slow relative to the processor, because it's an old display design, what happens is when you write a character or a command to the display, it actually puts it in a buffer, LCD out buff, and then every half audio buffer sent, which is just about 2/3 of a millisecond, it calls LCD do buff to send out the next command if there is one to go. So if there is a command to go, it sets the write enable high in there, waits a small amount of time, or the time it takes to calculate the samples, and then finishes the command, puts the write enable low. And I've created a child display hardware test function which currently just outputs the system clock time, and the system clock is just incremented every half buffer. Just a useful thing to have for using in timers. Shall we compile this code and see what it does? And go. And there we go. So now we are in a position to display our A to D conversion results. Alright, so let's get this A to D working. So we have a load of settings here. At the top here, which I've just not touched really, they're the default ones. Now it has regular conversion mode, where you give it a number of channels to convert, and it goes round and scans through them, and then goes round and round and round and round, and you have to set up a DMA really to collect the results, because there's only one result register. But in our case we want to scan our 2 channels, then change the multiplexing settings to move on to the next pots. So what I decided to do was use the injected conversion mode. So what we can do is set the multiplexing up, and then fire out the injected conversion, which will then convert the two, and you can convert up to 4 channels, and it has 4 registers, so you don't need the DMA. Okay, so we're going to we've trigger it by software. We'll trigger it when we tell it to trigger it, and then injected rank, I guess that's the priority, but we've set it channel 6 and channel 7, that's the one we want. Don't know what sampling time and injected offset are, they're just ones I've given it. Well, we might look at that in the future, or I will look at that in the future and just check that's sensible. But for now, let's just see if we can get the analog to digital doing anything. So let's generate our code. Okay, and it's ready to go. Okay, tried to set you up so you can see the display, and because the multiplexer's not working, this knob here is the one that we should get a value of, and the other channel, because I've only got one of these at the minute, I've just set a preset up just so I can set a voltage on it. And for now that will go. So I will go over to the computer and start it going. There we are. V1 and V2 are the two values from the A to D, and well, if I turn that knob, it goes from essentially 0 to 7F, the first one, and the second one changes value, which it shouldn't. It should be independent, but for now I'm not going to worry about that. So we have A to D. So now I think we should go on and try and get the multiplexing working. Okay, so the code so far is pretty simple. All I do is so this bit of code and this bit of code will be called repeatedly 2/3 of a millisecond apart. So this one I call this HAL ADC X injected start IT function, which simply starts the conversion off, and this bit of code I assume the conversion's done, and I just get the two values into val1 and val2 and pass them to the display. Simple so far, and not used so much now, but we are going to use it in a second. We get an interrupt when the ADC is finished, and I just set the GPIO pin when I called the conversion start and cleared it there just to see how long the conversion took, and it's about 3 milliseconds. But we are now, when it gets to here, going to move on to the next channel, set up the multiplexing and restart the ADC. So I shall write some code to do that, and I shall bring you back. Okay, I have this multiplexing code up and running, and all we do from here, the main loop, is call ADC start. However, I did discover that the display, the LCD control lines use port B, and the multiplexing lines are off port B, and the multiplexing lines are set in interrupt code, and the LCD control lines are set in non-interrupt code. So if the analog to digital conversions are running while the LCD is sending a command, both of them fall over considerably. So what I've done is the LCD do buff function is called, which sends out the next command if it's required. Then that finishes the command, LCD finish command, and then we start the ADC conversion. And show display hardware test just writes to the buffer, not actually to the display, so that's fine while the ADC is running. Okay, so we write the ADC results into a buffer called ADC result buff, and that has an ADC result index. So this first line we just make sure that's within the buffer, and then all we do is start the first conversion going. This is the interrupt function for the ADC complete. So we'll have two values which we put in our buffer, and then we need to move on to the next input. So we calculate the port multiplex value from the index. If the port multiplex is 0, we've been round one whole scan of all the inputs, so we just return. Otherwise, we start the ADC conversion again here. Okay, so does it work? Let us fire it down to the mean green and see what happens. Now there isn't a lot to see on the mean green at this minute, so we'll just stay looking at the computer screen. So we'll fire it up and we'll look at the scope. So the bottom trace is just the GPIO pin, which is high for all the time the scan is running, and the top trace is the analog input or the analog output from the multiplexer. So if I move the pots in turn, you can see it's sort of working, and that's the switch. It's sort of working, but we have a problem in that. So alright, say we're looking at this one, that we are switching here and starting the analog conversion also here. So what's it actually converting? Because we want that value, but we could be getting that value instead. But to the rescue, this parameter here, this sampling time, is the time it is sampling the input, and at the end of that time it closes off the input and converts what it's got, and we can convert that to up to 480 cycles, bearing in mind that the conversion takes 12 cycles. So if we increase that to a value where it's actually performing the conversion when the value has settled, then we should be good. So I am going to play with those values and bring you back to show you the results. Okay, so I've kicked out the sampling time to 56 cycles for both channels. Right, I've already incorporated that in this code, so shall we see how this one does? Okay, let's start it going and look at the scope. Okay, so we can see we could still go quite a lot further. That's 1 1/4 in 6 1/2. So 1.5 in 6 is really, it's about a quarter. So we could go considerably longer on the sampling time. Now if we go in here like that, we can see if we move the controls, so that's around 10 microseconds total, with 3 microseconds being the conversion time. So it's pretty stable, pretty flat along the top. So we get in there. So how does it actually perform? So this is the second one, that one, and this is the third one. Okay, it's going to be the second one changing that affects the third one. So the third one is at about a half. Around there. So let's see what effect the second one has on that. So that's 7879 to 7978. So it's not bad. It's not bad. It's about 1 in a byte's worth, which we're interested in. Is what we're interested in. And there's a fair amount of noise and dickering about as well, so we're going to put some smoothing on it. But shall we, just to see, kick that sample time out to maybe 3 times? So let's do it. So that's about 150, 144 will do. Okay, let's see what that does. Okay, so we could still go double that, I guess, but we'll see how that does. There we go. You can see even this one here is getting up to the top. So let's take our third one and that's good. That doesn't seem to change at all. Okay, well, I think we're going to go with that. I think we've proved that this multiplexing chip, this multiplexing idea works. So I'm going to order another of these little boards. I'm going to wire it in, wire the rest of the pots and stuff in, and we'll move on from there. So for now, I think we're going to call it time. Thank you for watching. Subscribe if you like us. Leave a comment if you've got something to say. A thumbs up would be nice. So and for now, it's goodbye from Triplicate, home of interesting electronics. Goodbye.